Everyone. So this evening we talk from Professor Alessandro Lunghi from the School of Physics, who's the principal investigator of the Quantum Materials Dynamics Group, and also my laid-out project supervisor. And this evening we'll be talking us through machine learning in physics, which is something that, between I suppose the physics courses and the TP course, we don't really see a lot of outside of external work. So hopefully we'll all be a bit enlightened as to what it is and how it's useful.
Cheers. Thanks a lot, Connor, for the introduction and for the invitation. Really glad I'm here today. The idea is to give you an overview of what we do in my research group, and I'll give an introduction of the main concepts behind machine learning and quantum science. I don't know if there is a specific format for this today, but I guess you can interrupt me anytime if you prefer. But anyway, this is the outline of the presentation. It's given in 4 different parts. I'll start with an introduction on quantum technology, then we'll see how machine learning can play a role in this field, and then I'll show you some applications. So we'll see how we can teach quantum physics to machines, if you want, and how we can fight decoherence in spin systems using computational physics. All right, quantum technology, it's a very general area of study, and loosely speaking, it's any application that exploits the rules of quantum mechanics, right? So it's a very large umbrella of phenomena here. And the idea is that there are many applications, if you want. So there are many applications where using quantum mechanics can actually help solving problems easily with respect to classical computing. So you see here a few examples, like quantum sensing. The idea is that we can use single atoms to probe properties like temperature, magnetic field to an unprecedented accuracy, right? You have communication. You can make systems non-hackable using quantum mechanics. Or quantum computation, you can speed up calculation by orders of magnitude using quantum hardware. And well, last but not least, fundamental science, right? So this is a great occasion to actually try to understand a little bit better what happens at the microscopic scale in atomic systems. So let's take a look at what we can do for quantum computation, like just an example. So there are classes of problems which are hard to solve, right? And they are hard to solve when they scale badly with respect to the size of the problem. So for instance, take diagonalization of a matrix. So if you increase the size of the matrix, it will become more and more costly to diagonalize it, right? And this problem here scales to the power of 3, which is not too bad. But there are also problems that they scale exponentially, meaning that effectively we cannot solve them on classical computers. And in the 90s, people started thinking about using quantum mechanics to solve these classical problems. And they demonstrated there are some problems that can scale polynomially and then become easy to solve on quantum hardware, on quantum machines. This is all in theory, right? So you're a theoretical physicist, you like this, but we also need to make a reality check and see whether we can actually do this. And people did try, and in 2019, the team in Google claimed to have reached quantum supremacy. So what this means is that they created an object, which is in this picture here. This is made of superconducting units, qubits, and you can use this to perform computation, and they show that you can take a problem which is intractable on a classical computer like this one's, and you can find a solution of the problem using this quantum hardware. Now you see here that this quantum processor here works at very low temperature, right? So it's just millikelvins, which is a big problem, right? So if you want to develop a quantum industry in general. And another problem that we have here is that the problem they solve is completely useless for human beings, right? So they just took a mathematical problem for the sake of the argument to prove the principle, but the problem itself is completely useless. However, just 1 year after that, they used the exact same hardware to solve the Schrödinger equation for a simple system. And solving the Schrödinger equation with quantum machine is something that it's really, if you want, the holy grail of quantum computing. So the idea here is that if we were able to solve the Schrödinger equation for very complex objects in no time using these machines, we would be able to calculate any kind of property of any kind of material we want to create and fabricate. So examples are drug discovery, right? So you need to simulate an entire protein and how pharmaceutical components interact with the protein. This is a problem which is hard to solve. If we were able to do it on a quantum machine, then we could design drugs in no time and no cost. Right, so this was to just give an idea of what are the applications out there when we discuss of quantum computing. So let's see what are the units of quantum computers, which are the qubits, right, the quantum bits. So essentially, any two-level system that behaves according to the Schrödinger equation could be a physical qubit. So if you have an Hamiltonian, you have two eigenstates, 0 and 1. You can take combination of them, and you can study their evolution in time. So for instance, here you see what will happen if you take a spin system, which is a prototypical two-level system, and if you create a coherence of the +1/2 and the -1/2 state. You study the dynamics, and you see the magnetic oscillation associated to the spin, like you see in that plot. And this oscillation is what are called the coherence of the system, right? And the coherence, if you want, is the hallmark of being quantum, right? So as long as you see this oscillation, you know that your system is quantum in nature, and that can then be used as a qubit for quantum computation. You go in a lab, you try to replicate this experiment, and you won't see the black line, but you will see the red one. So you see that this oscillation, they are perturbed by something, and they disappear after a very short time. So the system go in a transition from being quantum, behaving like the Schrödinger equation, to behaving like a classical object. So this loss of coherence is what we are trying to fight against. But where does it come from? So what I said is that the Schrödinger equation stopped working, which seems like I'm saying that quantum mechanics doesn't really describe reality, but that's not the case. What is going on here is that if we have multiple components in our system, like let's imagine this system made by system 1 and system 2, and if they are interacting, if I describe with the Schrödinger equation the entire system, everything works. That's an isolated system, the Schrödinger equation applies. However, if I just try to focus on one portion of the entire system and apply the Schrödinger equation is not a good description of this anymore. So we always need to refer to isolated systems. And this is the common case in reality. So your spin or whatever qubit you have is never completely screened from the surrounding. There will always be some interactions. And these are the interactions that limits coherence, that makes disappear those beautiful oscillations, and this is what we need to fight against. And that's the reason why people in Google were cooling down their Sycamore hardware to millikelvins, because reducing the temperature reduces the amount of perturbation coming from the external world. So how can we understand how decoherence works and what we can do about it? With repetition myself, so what I like to do in my life is to take the Schrödinger equation, implement some software and try to solve it numerically and get an understanding of what happens in real systems and materials, right? And this is a well-established field of computational physics. And we use classical computers because that's what we have. And there are algorithms that can give you, in principle, the exact solution to the Schrödinger equation that would give you access to all you need to understand about decoherence, right? You can always describe the interaction between your system and the environment by simulating it. However, if you want to get a very accurate description, as you see in this plot here, the computational cost of your algorithm would grow exponentially. It looks like we are kind of stuck here, right? So we are trying to use classical computers to solve the Schrödinger equation to design a quantum machine which could then be used to solve the Schrödinger equation. So we are in a difficult situation. However, there are still things that we can do in classical computing to speed up this process and get a good solution of the Schrödinger equation. And this is what leads me to the second part of the presentation, and we can discuss what machine learning can do for this field, for instance. So before getting to machine learning, what is conventional programming or computing? So what you do, you create your algorithm, right? So it's a list of instructions. They are hard-coded in your software. So there is a developer that thought about the algorithm and wrote it down. You have a set of variables and conditions that change the states of the variables, and you execute the code, right? This is great. You can, in principle, code whatever algorithm you want to solve whatever problem you want. One of the big obstacles of using conventional programming is that these codes are rigid. They are not flexible at all. So if the problem you give to the algorithm is more complex than what you thought at the beginning, you need yourself, the developer, to sit down, understand the problem, and change the software in order to solve the problem, right? And this is time-consuming, right? And especially it's kind of non-convenient because you need to sit there, you need to spend time to solve the problem. In principle, we would like machines to solve these kind of problems by themselves. We would like machines to understand where the problem is in their own software and solve it. So in principle, we would like machines to work as human beings do, right? So we can understand where a problem is, sit there, think, and take action. So we go to word of reference and we see what to learn means. So it says that it's to gain or acquire knowledge of or skill in something by study, instruction, and experience, which is something you're familiar with, I'm sure. So like if we take the first two keywords, study and instruction, that's logical. So like if you want to learn how to play a game, give you a set of rules, you're able to understand them and then apply them to the case at hand, right? So you can play against an opponent and try to win. Which seems easy, right? So you have a very small set of rules you're trying to apply, and yet even just to explain this to a machine, it took decades to computer scientists to do that. And like only 1997, a computer was able to beat the world champion of chess, Kasparov, at the game of chess. And that was a big deal for computer science. It was the first time that they could prove that artificial intelligence or a computer can learn from experience and beat a human being at something like the game of chess. So if you can do that, you would think that, well, you understood how it works, you can do anything else. It's not that simple. It took another 20 years to beat the world champion of Go, to the game of Go, right? So still remaining in the realm of games, it took another 20 years to understand how to do to a game. Now, there is another fundamental ingredient in learning that we would like our machines to have, which is the experience, the ability to exploit experience. Now, humans, of course, use it all day long since early age, and that's clear why biology selected this for us, right? So think of a humanoid in the jungle, they saw a jaguar, they saw the friend being eaten by the jaguar, and they learned by the experience that it's not great to be in the surrounding of a jaguar. So they learn by experience, but also it's important that they can extrapolate this to new contexts. So you have experience of a jaguar, but then when you see a panther, you're able to understand that there's something similar and that your response should be similar as well. So this is another trait that we would like to pass on to machines and algorithms. So it seems like the human beings are great at learning from experience. So let's see at biology if there is the key to understand how we can transmit this property to machines. So our brain is where everything happens. So if you look at what the brain is made of, it's just a gigantic net of neurons. And the neuron itself, it's a relatively simple object from a biological point of view. So what happens here is that you have many neurons connected to other neurons. Each neuron will send a signal to other neurons. And if a neuron receives many signals above a certain threshold, it will send itself a signal to another neuron. So you create this sort of cascade of signaling inside the brain, and depending on the property of each neuron, you will have different processes like this. And computer scientists indeed try to reproduce this with a simple, let's say, expression. So you see here the output signal of a neuron, the capital S, is a function of all the signals received by the neuron weighted for the property of the neuron itself. And this is what is called the perceptron. So we can use this and try to build an artificial neural network. So what we do, each node will correspond to a perceptron, so the function we just saw. And then we connect all of them and we let the signal proceed inside our net. So if you see here, we will have some input signal that in biology will correspond to our interaction with the external world, right? Our senses. And this signal, depending on how the nodes are connected and on the property, they will lead to a final output stimulus that will correspond to some action or feeling. And in machine learning, we do exactly the same thing. So we get our Fisher vector that will represent the property of a function, and we get to the end after processing all the nodes, that we get the value of the function we want to estimate. So until now, this is just a complex mathematical object, right? So why is this useful? There is a theorem, which is called the universality theorem, that says that this sort of function here can adopt any other function. So whatever function, as complicated as you want to have in mind, and you want to try to reproduce it with machines, a neural network will do the job. Now, it doesn't say anything on the complexity of the neural network. It might be that you need 6 billion of nodes. You don't know that. But in principle, there is a neural network that will approximate your function with whatever accuracy you want. So how you do this? Essentially, you show the neural network examples of the functions you want to recreate, and you train the neural network to reproduce it. So you change all the weights inside the nodes, and you try to predict the output from the example you show to the neural network. And this function here has been applied in physics in gazillions of different cases, right? So I'll show you now one example which is related to the problem we were discussing before, so solving the Schrödinger equation. So as we mentioned before, we have the problem, we would like to solve the Schrödinger equation for many different systems and also systems which are very large in size, right? So what we need to do in principle is to take the Schrödinger equation in the Born-Oppenheimer approximation. So you see the first line there is the one describing the nucleus, or the nuclei, if you have many. And the potential energy that keeps the nuclei together is the electronic Schrödinger equation, the second line. So even for a simple case like the hydrogen molecule, which you see the plot there, if you want to reconstruct the profile of the energy with respect to the bond distance, you need to solve the Schrödinger equation for the electron at each distance between the atoms, which is very expensive, right? The idea here is to completely forget the electrons and find a proxy to describe the function there. Well, it's not so easy, turn out. So people have been trying to do this for decades. And all the models until very recently were not accurate at all. Well, it's easy for a hydrogen molecule, but if you try to take a protein or a complex molecule, then it becomes almost impossible to do this. And this is where machine learning can play a role, for instance. So what we're trying to achieve here is to, let's say, we take a water molecule there, we input the coordinates into the Schrödinger equation, and we diagonalize the Hamiltonian, we find the ground state, and that gives us the energy. Then let's say we encounter a new conformation, and we do the same. Input the structure into the Hamiltonian, and we find the energy. So this solving the Schrödinger equation, as a matter of fact, it works like a function, right? So your energy will be a function of your coordinates. And what you're trying to do with machine learning is to learn this function just by looking at a few examples. And indeed, this can be done. So for instance, you need to generate a training set, so this list of examples of relation between structure and energy. And if you try to teach this to your machine learning model, you can come up with an expression, an analytical expression that connects the structure to the energy. So we try to do this in my group, and we use a very simple expression which looks at the end as a linear regression, if you want. So we have that the energy is just a combination of structural parameters times some parameters which are unknown, and these will correspond to the weights inside the perceptron. So you show to the machine learning model many examples. So you see here the number of configurations and the number of examples we show to machine learning. And the error that the machine learning does in predicting the energy, which will be the blue curve, will diminish progressively. So this means that the machine learning model is learning to predict the energy. If you just show 10 examples, well, it will give you a rough idea of what the energy of a new molecule could be, but it won't be great. And if you show it 600 examples, then it's now able to get right the energy of any new molecular conformation. What's the good thing here is that if you want to do this calculation, solving the Schrödinger equation brute force, it might take hours. You might need a large computing facility. Once you have trained your machine learning model, you can do this on your laptop in fractions of milliseconds. So after training, we can use this to do any kind of physics we want. We have played with different systems. So like this works for molecule, works for chemical reactions, works for 2D materials, ceramics, and whatnot. And just to give you an idea, these are 3 applications that we work on together with Stefan van Beet as well. So you see there, we train a machine learning model to predict the energy of 2D materials. And this allowed us to study superlubricity in this heterojunction. So we have these 2 layers to the material sliding on top of each other. And we can now do this calculation very quickly on classical computers, while doing the same brute force by solving the Schrödinger equation would be absolutely impossible. Another example here, we have a molecule in solution. So we can simulate the molecular dynamics in solution, including all the solvent, which again is another kind of simulation that would be impossible brute force. And the last example here is the study of how temperature affects the thermal properties of ceramics. So this is zircon diborite. So material can be heated up to thousands of degrees without cracking. And here we're able to reproduce the experimental behavior of the lattice structure as function of the temperature. All right, so let's see what these kind of algorithms, this kind of application can be used to fight against our initial problem. So how to fight decoherence in quantum systems. Now, the quantum systems we study in our group are spin systems. As we were mentioning before, spin is the sort of prototypical two-level quantum system, right? So that's a good place where to start. Now, what kind of actual system behave like a spin one? We need to start from the beginning. So let's say we take any chemical element that has unpaired electrons. And if you have unpaired electrons, it means that you have a total amount of spin in your system which is not zero. And usually you just need to take a transition method, the first row of the transition methods of the lanthanides. And those are typical cases where all the spins are not paired up inside the atomic orbitals, and at the end you have some sort of giant spin as residual. And those are our, let's say, physical qubits, spin qubits. Now, of course, the story is not so simple, so you need to go beyond the description of just the magnetic ion. You need to include the surrounding as well, right? If you remember, we were discussing that we are always dealing with a quantum system connected to some, let's say, environment. And our environment will be made by other atoms in general, right? So think of the ion to be inside a solid state object. You will have some coordination due to the atoms in the surrounding. But anyway, even after all this complexity, if our system still has some unpaired electron, it will behave like a spin qubit. And in my group, we deal mostly with molecules. So you can connect different ions in very weird ways. People from chemistry played around with this for decades, and they came up with all possible structures. So you see here that you have some rings where you have these green ions, and they're all connected together, but at the end they kind of behave as a total spin 1/2. And you can play with this and change the ligands, change the ions, and you can really explore a very large amount of phenomena. And the beauty of this is you can now use them for doing quantum operations. So you can like absorb them on the surface and use the spin to probe what's happening in the surrounding. So like in this third on the right object here, in this picture, people did use a molecular spin absorbed on a superconductor to study the dynamics of the Hooker pairs. So this is something done locally at the atomic level, which is impossible by any other means. Or in the picture in the middle, people sandwich just one molecule between these two gold leads that act like electrodes. And by making current flow through the molecule, they were able to manipulate the spin and perform quantum computation. So like this experiment here had been done in one lab and never been replicated anymore. Even just the work to place one single molecule there, it took probably decades. But anyway, this is possible if people is working on these kind of things. So let's see now what happens when we have a molecule interacting with all this surrounding, right? You have your surface, you have your currents, and these create some noise and will lead to decoherence. So we are back to the slides where we have our system. We are just looking at our molecule, which will be QM system number 1, but these will always be interacting with the surrounding. And we want to understand how this flow of information occurs. So what actually happened in a spin system? So we have two states. Let's make it simple. Let's suppose we have a spin 1/2. So we have an external magnetic field that removes the degeneracy. So we have spin plus 1/2, which is lower in energy, and spin minus 1/2, which is higher. Then we want to perform some quantum operation. And this is usually done by using microwave pulses. And let's say we move population from the ground state to the excited state. If everything behaves according to the Schrödinger equation, the system would stay in this place where we put it. However, there is this interaction with what is called a phonon bump that would make the system relax. So the system trying to go back to the equilibrium by exchanging energy with the thermal reservoir. Now, if you're not familiar with it, phonons are just vibration of the atoms inside a solid state lattice. So the atoms, due to temperature, they would oscillate according to an harmonic oscillator physics. and these can interact with the spin and cause relaxation and decoherence. Usually the time it takes to relax back to equilibrium is called T1, and that's the time we would like to extend as much as possible. We like our system to behave coherently as long as possible. All right, so we can use quantum mechanics to describe this process here. The expression looks horrible, but we have the Hamiltonian of our spin system. We have the Hamiltonian of our bath, which is just the sum of harmonic oscillators. And then we have an interaction term, which is the spin phonon coupling Hamiltonian, to describe how easily energy can be transferred from the spin to the lattice. And then we can put everything inside the Schrödinger equation and get some level of approximation to describe the dynamics. And these are the equations we use to describe this process here. Now, they look complex. Let me just describe the physics behind this. So we have a first degree of approximation, first order time-dependent perturbation theory, which describes the following process. So the spin, when it's interacting with phonons, can always exchange a quantum of energy with it, as long as the phonons are in resonance with the spin. So you may have a process where the spin undergo a transition from +1/2 to -1/2, and the phonon will undergo the opposite transition, so you lose a phonon, or vice versa. You can emit a phonon, and the spin system will undergo a spin flip. You can also have multi-phonon processes. It becomes even more complicated. So instead of having one phonon transition at the same time as the spin transition, you have multiple phonon transition at the same time. So in this example here, you have a phonon which is emitted and a phonon which is absorbed at the same time as the spin makes a flip. And these are the sort of quantum processes that undergo continuously in solid state for a spin system. And these are the processes that cause decoherence. Right, so we understand the physics, we know what are the processes, but we still need to be able to compute them if we want to understand how to deal with them. And this is what we do in my group. So we use quantum mechanics to estimate all the parameters that describe the system, the path, and the coupling between them. And this is a big challenge because there are gazillions of them. So here I'm gonna just show you a couple of examples for wrapping up. This is a molecule that behaves like a speed 1/2. So there is just 1 ampere electron on that molecule. And the molecule, of course, can interact with the external field with a Zeeman interaction, but there will also be other spins in the surrounding which are like causing magnetic decoherence as well. And we can compute all these things using quantum mechanics. So we can compute all the frequencies in the lattice, we can compute all the terms in the spin Hamiltonian, and in principle we can also compute all the coupling terms. Now the coupling terms are defined as the derivative of the spin Hamiltonian with respect to the atomic displacement. So if you want to compute it, what you will do, you calculate your spin Hamiltonian coefficient, 8 to 2 in this case, as function of the displacement, for instance, of the vanadium atom. So you get a few points and you just calculate the first order derivative. Easy enough. You want to calculate the second order derivative, it's more or less the same principle, you just do a two-dimensional scan on two different variables. Now the problem here is that to just get 1 point on this plot, it might take a few hours on a good computer. So when you try to replicate this two-dimensional plot for hundreds or thousands of degrees of freedom, the number of calculations you would do would take eternity. And this is exactly where machine learning can play a role. So instead of brute forcing calculating all these points, what we do, we first teach machine learning to predict these quantities for us, and then we ask machine learning to do all the numerical derivatives for us, saving us years of time. Right. One last obstacle before getting there. Now, we would also need to teach machine learning to predict these sort of properties here, which are tensors. And tensors are hard to deal with because they need to rotate in a very specific way. So to make this easy, if you want to predict like the dipole moment of a water molecule, we have the condition that on the top left, if you flip the water molecule in space, your dipole moment will need to flip as well, right? That's what you would expect. But if you never taught that to machine learning, if you flip your water molecule, machine learning wouldn't understand that and will still predict the dipole moment to be oriented in the same way, which is a problem for us, right? It's not a physical description of what's going on. So we have been working with Annie in my group to solve this problem. And we came up with this strategy here, where our tensor is described as a series not just of scalar structural properties, but as a function of spherical harmonics, which behave in the right way. So if you do this, in fact, you can learn all the tensors you want. Like here, we were trying to predict the magnetic anisotropy of cobalt molecules, which behave like a second-rank tensor. And you see here, we can match the predictions coming from quantum dynamics, and we can make excellent predictions. Right, so we know how to compute all the terms describing the spin and its interaction with the phonon bath. We can now solve the Schrödinger equation for our spin, and we can calculate how T1 changes with temperature, for instance. And as you see here, we have the simulation comparison with the experimental value, and they follow exactly the same trend, which guarantee us that we now understand the physics behind spin decoherence, and that we can now look at the details of it. You can think of doing this also for more complicated objects. This is a dysprosium compound. You have 16 spin energy levels in this compound here, which is a horrible thing even to think about. But nonetheless, applying the same strategy, you can predict how the relaxation time, your coherence time changes temperature, meaning that you can now look into the details of the bath coupling and understand how to improve coherence. All right, so to wrap up, I gave you a general overview of what are the things we do in my group. So we start from open quantum system theory. We try to understand how the quantum dynamics of an object evolve in time when it's interacting with surrounding. We approach this problem from electronic structure theory, so we are able to do the calculation for all these parameters, which would lead us to a complete description of spin phonon relaxation. And then I briefly sketch a way that we can use machine learning to speed up these calculations and eventually lead to materials design. Well, thank all the people in my group that need to suffer me, including the fact that I take pictures without telling them. And then before concluding, I think it could be interesting for you to know what are the opportunities out there in case you're interested in joining research projects like this. So in the School of Physics, you might be aware that we run internship programs during the summer. So you can ask myself or other PIs in the school if there are positions available. These are usually running just after the end of the exams for 6 or 10 weeks, depending on the availability of people. There are PhD scholarships. So like the Irish Research Council, every September, October, they open a call for people like you that can submit a project in collaboration with the PI in the School of Physics to ask for money to support you through a postgraduate program. However, if you're not, let's say, research inclined, but you would like to, let's say, get into quantum science, but from an industry perspective, we also run a one-year taught master in the School of Physics. We just started doing this year, and it's going great so far. And we try to cover essentially all the steps behind quantum science. So there will be teaching about the foundations of quantum information theory, open quantum system theory, quantum simulations, up to the physical implementation of quantum systems. And last but not least, we also have an extensive program of industry engagement. So we try to get you as close as possible to what people do in startups and in companies in this area. And this is an example we are really proud of. So we are collaborating with this startup in Finland. It's called Algorithmic. You see here Prof. Alessandro, the CEO and co-founder of it. And they just started in their, let's say, their work, but they already received more than 4 million euros to fund their startup. And essentially what they're trying to achieve is to create this comprehensive set of software and codes to develop quantum algorithms and perform quantum computation. And we are collaborating with them to the level that we can offer multiple internships in Finland in their group to study with them and work with them. And in addition to this, we have multiple people coming from all over the world to explain to you what they're doing with their startup, as well as giving lectures to explain you in detail what you will need to know to work with them. last but not least, for the ladies, we also have this initiative here, which is in collaboration with Microsoft. So we have at least 2 funded scholarships to participate into the Master in Quantum Science every year. So you need to apply for this, of course. I think it's a great opportunity if you're considering to this path for your future. And here we have the winner for the last year, which are currently enrolled, Jabara and Matea. And they also told me that if you want, I can put you in contact with them if you have questions for them. Good, and this leads me to the end of my talk. Thanks for your attention.
So, does anyone have any questions?
There's many applications of quantum computing and lattice QCD.
I'm pretty sure there are. I'm not aware of them. It's not really my area of expertise, but I mean, quantum computing at the moment is really booming in the sense that people is kind of thinking to find application pretty much anywhere. So you mentioned lattice QCD, right? Yeah. So I guess that's a flavor of solving the Schrödinger equation or some equations for that specific system. So I would guess that there is people working on that as well, exactly as there is people working on applying the Schrödinger equation to on quantum machines.
I was just wondering, how does your implementation of decoherence differ from the likes of E3 and M libraries?
It's simple. So what they do in those libraries, they use very complicated architecture. I really don't know why I actually asked the people working on those, and they didn't come up with any good answer, in my opinion. But the only big difference is really the complexity of the architecture. So we are using the same building block, let's say, so this transformation with the spherical harmonics that gives you the right transformational properties. But apart from that, that's more or less the same kind of idea. The only difference is that our model is linear, meaning that you don't need many points to train it. So you can get away with a few hundred points as a reference. But when you look at those models there, they have gazillion of different parameters, meaning that you need to use several thousand of examples to train them. At least that's the difference. So I would say if you have a simple system you want to play with, I would go with my model. So this is linear, it's very easy to deploy for application. If you're trying to apply this to all the configurational space, you probably need the complexity of this kind of algorithms there. But I would say it's the same difference from using a linear model of a neural network, right? So it's the same thing, you're just increasing the complexity of it and the non-linearity of it, so it's more flexible.
Is your approach graph-based?
No, I wouldn't say it's graph-based. So we just sum on all the atomic contributions that you do for So you have each atom will contribute to your final property to some amount, and each atom will contribute with the spherical tensor in that case. So it's not really about let's say the distance between atoms. You don't take into account the let's say the bonds or this kind of things here.
Do you see quantum machine learning as something that will require us to tackle both the quantum computational problems and machine learning problems, or is something that's achievable, I suppose, in line with normal machine learning and quantum computation progress?
Now, so first, before applying to this, it should be said that quantum computation, or let's say quantum algorithms in general, they are known to work better than classical one on just a few problems, right? It's fully demonstrated only for a few problems. So solving the Schrödinger equation or the Scholl algorithms, those are cases where we know that the quantum algorithm will outperform the classical one. We don't know yet whether other classical algorithms can be run more efficiently in quantum machine, and there is a lot of people trying to understand the limits of this. So there is a lot of people trying to understand whether we could use the machine learning algorithm, translate it into some quantum algorithm and make it faster. As far as I know, there is no evidence at the moment that quantum machine learning can outperform classical machine learning. it's kind of true the vice versa in the sense that there is a lot of activity in trying to use machine learning, classical machine learning, to perform quantum computation more efficiently. So it's sort of an aid to quantum algorithms to speed up even more the calculations. But there is a lot of work in the area. So there is people trying to adopt quantum computation to finance, to biology, to pretty much anything. I think the jury is still out on that.
Any more questions? Okay, if not, then thanks again for giving this talk.
Thanks to you guys. Cheers.
Thank you all.